Hi everyone, and welcome to lesson 2 in week 2. Last lesson we talked about the properties of circuits, including potential difference, current. We talked about electron current, the flow of electrons, and then that weird conventional current, which is the flow of positive charges. And lastly, resistance and the resistance of a light bulb. Today what we're going to do is we're going to talk about how these three things connect to each other, okay? We're going to talk about how potential difference determines current, how resistance determines current, and how all three of them really can interact with each other within a circuit. So let's go ahead and get to it. We're going to start with the demonstration, set up an aim, and then explore the content. Okay, everyone, so here I have the setup from the last lesson. Just a reminder, I have this little piece of metal here, which I say completes my circuit, right? When I have this metal here, I allow my current to flow from the positive, right, into my switch, which is now closed, through the light bulb, through that, remember that metal, the metal outside, into the bulb itself, where there's what we call the filament, down into this copper wire to here, over through this portion, up around to here and down into the low terminal. So I've connected my high and my low potentials, giving me a potential difference across the bulb, allowing the bulb to illuminate. But as I said in the intro, what we're going to talk about is how potential difference, current, and resistance relate to each other. Well, to do that, what I'm going to need to do is build a circuit where I can change these things, right? So let me draw out what a circuit like that would look like. Well, my circuit here really looks like this. I have a battery, which is my source of potential difference. It goes over to my switch, like that, then over to my bulb. Now this is the circuit symbol for a bulb. Forgot to draw that on the last one. Maybe I did, I don't remember. So my bulb, and then out there, down to my battery. So this is a proper circuit diagram for what we're looking at up here. Notice the difference, right? If I drew this, it would be a mess. You're probably having a hard time following it right now because in order to get this circuit to be functional and accomplish the goals that I wanted to accomplish, I had to make it look kind of ugly, right? And deal with the materials that I had available to me. If I gave this circuit diagram to you at the end of this unit, I would expect that you'd be able to recreate something like this, knowing how all these things connect together. All right, so I have my potential difference of the source. I have the resistance of my bulb here. And I know that when I close this switch, I'm going to have a current that's flowing like this, right? And it's going to flow around like that, around my circuit until it returns to the low potential side of the battery. So there's my current flowing around. Well, first thing we're going to want to do is let's go ahead and test the effect of Vs. So we're going to ask, what happens if I change Vs? What happens if I change it? Well, what are some options? Well, if I change Vs, will I be able to change the resistance of the bulb? Well, the answer is actually no. The resistance of the bulb is a physical property of the bulb itself. So that is something that's going to be unchanged for this demonstration. But what I can change is the current. So ultimately we're going to ask, how does changing the potential difference affect the current of the circuit? Okay. Well, in order to do that, I'm going to have a way of doing that. In order to do that, I have this thing right here. This is a potentiometer. It will allow me to adjust the voltage that's coming out of the battery. I just need to quickly set this thing up. Now this potentiometer is not really meant for the currents that we're going to get, so there's a chance that it will burn up as I use it, but hopefully we'll get through a little bit. Oh, let me turn the switch off. All right, so my potentiometer is now integrated in my circuit, excuse me, and I can turn the knob on the potentiometer in order to adjust the potential. what we're going to be measuring as we adjust that potential, or what we're going to be observing, is the bulb. The bulb will tell us about current. And what I'm going to tell you, and I'm not going to prove this right now, we'll get to it later, but I think intuition tells us that the brighter the bulb, the greater the current. Right? If I pump more current through a bulb, it's going to be brighter than less current. So to do this, let me flip my switch. Let me start with the potentiometer like that. Okay. Now I'm going to increase the voltage. Okay, there it is, right? Very low voltage. I'm going to increase it. Let's see what happens to the brightness. There you see it getting brighter, right? Decrease the voltage, it gets dimmer. Increase the voltage, it gets brighter. Well, I'm going to turn it off because I can smell the potentiometer starting to smoke up. What we're seeing is that as I increase my potential difference of the source, my battery potential difference, the brightness increased, and therefore the current increased. Okay, so that's one relationship that we've been able to establish. Now, get that potentiometer out of here, return to my regular circuit. Don't have to worry about anything catching fire now. My next question is going to be, what happens if I change R? Well, as I said before, I cannot change the resistance of the bulb. That's not possible. But what I can do is change the resistance of the circuit. If I change the resistance of the circuit and the bulb gets brighter, if I increase the resistance and the bulb gets brighter, that means resistance increase the current. We know that's not what's supposed to happen, but let's actually observe it. Here I have this wire. This wire basically has no resistance for our purposes. What I'm going to do is I'm going to replace it with this right here. This is a resistor. I just got the camera to focus here. Okay. This here is a resistor. Each of those little bands tells us what the value of the resistance is. I did not look it up. I don't remember those values, but if you're curious, you can look it up on a table online. And what I'm going to do is I'm going to take this resistor and I'm going to place it here in place of the wire that was there before. Let's see what happens to the illumination of the bulb. Okay, so you can't see it. Let me turn the light off. Okay, do you see that little orange light at the top of the screen? That's actually that same bulb. It's still lighting up. There's still a current going through. It's just so incredibly dim. Ready? I'll put my hand over it. There it goes. Okay. And that's because I've increased the resistance of the circuit by putting this resistor here. So I'll take that off. Ooh, it's hot. And drop this one back on there. Okay. And it's bright again. So here we see that if I increase my resistance, let me turn this off, right? I decrease my current. Okay. So there's our relationships. Let me move this out of the way. Okay. So here are our findings so far. What we've discovered is that in a circuit like the one drawn here, as I increase my voltage source, I increase my current. So I can therefore say that the voltage source is proportional to the current, okay? Now, of course, we don't know the ratio. I'm just going to tell you that it's proportional. Then we saw that as I increase my resistance of the circuit, I decreased my current. Well, this seems to be the opposite, right? It seems to be that as resistance goes up, my voltage goes down. And keep in mind that the voltage of the source for the circuit as a whole stayed the same. And so this brings us to what's called Ohm's Law. Okay. Ohm's Law is going to be the most important equation that we deal with in this unit. Think of it as like the Newton's second law of the circuit's unit. And what it is that delta V or the potential difference, is equal to, right, I, the current, times the resistance. Okay, so the potential difference is equal to, I'm going to circle that in blue because it's so important, the current times the resistance. And so we see that relationship. If I increase V and R stays the same, I has to increase, right? If I increase R and V stays the same, I has to decrease. In other words, if I increase V, the bulb gets brighter. If I increase R of the circuit, the bulb gets dimmer. And I am actually skipping a little bit about the second argument here, but we're going to talk about that a lot coming up in just a moment. So that is Ohm's law, and we're going to do lots of practice. But before then, I want to talk about that bulb, right? And the brightness of that bulb is really the electrical power. Uh-oh, I'm dying there. Hold on. It's the electrical power okay, or capital P. This is the same power we've learned before, okay, just regarding electricity instead of mechanical energy. Oftentimes, the words that we're going to be here used in terms of electrical power are going to be things like expended. So what's the power expended by the bulb? We can hear the word dissipated. Okay. The word used. Okay. The word lost. Right. Anything like that is referring to the electrical power. So a word problem could be like, find the electrical power dissipated by a resistor, something along those lines. Going back to our equations, well, we know that power, when we're doing mechanics, is work over time. You also found in last week's lesson that work is the charge times the potential difference, didn't we? Over T. Well, let's look at this. I'm going to separate a little bit. Q over T times V. Well, what's Q over T? That's current, isn't it? Charge over time. That's that. Remember, the charge is passing through some cross-sectional area. So we have I times V. So I can say then that the power is equal to IV. But suppose we have a problem and we don't know V. Let's say we only know I in the resistance. Or on the other hand, imagine we don't know I. Imagine we only know V in the resistance. Well, we have Ohm's law, don't we? Okay. Ohm's law tells us that V is equal to IR. And I know I'm losing my delta. I'm going to start doing that. When I lose my delta in circuits, I'm really still talking about potential difference. We never really talk about a circuit with just potential, because if it's a uniform potential, nothing really interesting is going to happen. So if I put V, I'm really talking about delta V. Okay. Well, I can say V is equal to IR, or I can arrange this and I could say I is equal to V over R. Right, same equation, just rewritten. Well, then can't I write that P is equal to, well, I could plug V in here, I squared R, right? And can't I do P is equal to, well, let me plug this in here, V squared over R. These are all fair equations for electrical power. Okay, they're all true. Now these two are a little bit tricky. Okay, we're going to choose which one based off of what's held constant. So this is going to depend on if I or V is held constant. Right. And we're going to do lots of problems. I know I've introduced Ohm's law and we haven't done any practice. I'm introducing electrical power and I'm just telling you this is true. I'm doing this all in the interest of getting two problems and then actually talking through what we're establishing now. So let's just quickly do a basic electrical power example, which I actually already wrote out for the sake of time. Okay. So the question is, what is the electrical resistance of a bulb designed to dissipate energy at a rate of 60 watts? Remember, power is the energy per unit time. So if it's dissipating energy at a rate, that's really another way of saying power. At a potential of 110 volts. So what does this mean? Well, 60 watts, 110 volts. This is just a regular old light bulb, isn't it? Right? This is the light bulb that you probably have in your kitchen, something like that. Those, say, 60 watt or 25 watt or 100 watt light bulb, that's all read in terms of 110, because in America, we know if we put a 60 watt bulb into an outlet, into a socket, excuse me, it will experience 110 volts. So how do we go about solving this? Well, we have our three equations. Which one do we want to use? Well, we don't know current, so we can't use these two. Let's look at this one. P is equal to V squared over R, right? That is going to be 110 volts squared over, wait, I don't know R either, do I? That's a problem. Oh, I'm not solving for that. I'm solving I'm solving for R. So over R, I can rearrange this and get that R is equal to 110 volts squared over my power of 60 watts. And if I plug in, I find that that's 202 ohms. Okay. So there you go. I'm really just plugging into this equation here to solve for the resistance of the bulb itself. Now, when we talk about the resistance of an object and Ohm's law, there are different types of resistors. Some, like the bulb that we discussed here, right? And then some that are like the resistor that I put on that circuit before, like this right here, right? This resistor is actually made of sort of a ceramic. If you could feel it, you would know that. And that's ceramic so that it can hold more heat and dissipate heat faster, okay? So it's able to get rid of the heat that it develops as current flows through it. It does that because we want to have that resistor's properties, the physical properties, unaffected by the temperature. So we call that an ohmic device, okay? And an ohmic device is an element that's a circuit element with a constant resistance. Okay, so because the ceramic is able to dissipate the heat quickly, it's able to maintain an approximately uniform temperature, not exactly, and therefore it maintains a constant resistance. If I change the temperature, I would in fact change the resistance. So this is designed to be an ohmic device. If we look at a circuit that this resistor is in, let's say it looks something like this. That's my resistor. I can change the voltage of my source and measure the current coming out of the battery. We'll talk about how to do that in a little bit. I can then produce a graph of potential difference versus current. And if I have a true ohmic device, what I would find is that the slope of this graph looks like this, or it's constant. Well, let's look at it. What is the slope of this graph? Well, it's V over I. Well, Ohm's law is V is equal to IR. V over I is R. That's the resistance. So the slope of a V versus I graph will give us the resistance of whatever the thing we're measuring V and I for is. So if it's ohmic, we can say it has a constant slope for a graph like the one below. But what about something that's non-ohmic? Well, this is going to be the opposite, right? This is going to be an element with a changing resistance. Great example of an ohmic device, a light bulb, right? Have you ever tried unscrewing a light bulb from the socket? It gets very, very hot, right? This thing gets incredibly hot. Well, as it increases its temperature, as we increase the temperature, what we find is that we actually increase the resistance. And so if we create one of these graphs of V versus I for an object like a light bulb, what should be happening? Well, as I increase the current, I'm going to be increasing the temperature. It gets brighter, right? The brightness and the heat are very related to each other. Increase the temperature of the bulb, which means I increase the resistance. The slope is the resistance. And so I think you see where I'm getting at here. The slope must therefore increase with time, or excuse me, with current. So this is an increasing R. It's a non-ohmic device, has a changing resistance as that temperature goes up. Now, for the sake of my demonstrations, bulbs allow us to see what's happening really well. So we're all more or less going to treat this as an ohmic device in a circuit, because we're going to be looking at that circuit at a point in time when the current isn't changing. We're not going to be plotting current versus voltage. But if we did choose to do that, we would find a relationship like this. But when the circuit is just set at a constant voltage and a constant current, we can treat them just with Ohm's law as we normally do, and that's what we'll be doing with the demonstrations ahead. All right. So I know I'm covering a lot. Again, this is all in the interest of getting to actual problems. And please come to the lesson recap with any questions that you have as we go. Now, we've covered Ohm's law, we've covered power dissipated by an object, specifically bulbs. We've talked about ohmic and non-ohmic devices. The next thing we're going to talk about are electrical meters. So for us, this bulb is sort of serving as what we call an ammeter, a meter that measures the current, because it's informing us if the current in the circuit is increasing or decreasing, but this is not giving us a quantitative value. This isn't giving us a value of amps. We're just using it to conceptualize what's happening. A true ammeter will actually tell us the value. Okay, so the ammeter, I'm going to put it down here because I'm going to draw some circuits up above there. Okay, this is going to measure the current in the circuit. Okay. We also have a voltmeter, which, as the name would suggest, is going to measure the potential difference in a circuit. I'm leaving space deliberately because we're going to have to add some information about them. Now, I'm going to divide this in two. And I'm going to draw a circuit. My circuit here is going to start with a battery that looks like this. Okay, and it's going to go up like that, over, down to a resistor, and then back to the battery. This has a voltage of, let's say, Vs. Okay, and the resistor has some value of R. What I want to do is I want to return to this gravitational analogy. Okay. Well, say that this is like some ground level, okay? This is, yeah, I'll just write ground. And over here, we have a lake. And what I want to do is I want to get the water in the lake to the top of the mountain. Okay, I want to lift it up some height to here. What am I going to do? I'm going to build a pump, right? I'm going to build a pump here. I'm going to put a pipe all the way up to the top of the mountain, like this. And then I'm going to turn that pump on. The water is going to go up it, and then it's going to flow on down the mountain, right? Back to the ground level. Well, the reason why I'm drawing this is because this is analogous to the situation here. When I have the pump on, that's sort of like the battery, right? This is the low, this is the high. The water starts at the lowest level, the lowest potential energy. The pump gives it some delta V, doesn't it? It lifts it up, it gives it energy, more and more and more energy. Then it reaches the top, it's at the high potential. It then flows through, down. We can look at this hill as sort of like the resistor if we want to. Okay? It flows down until it reaches the other side, right? It reaches here and then it's back at ground level. It's back at the low, right? So pumps it up to high, goes down the resistor to low. Pumps it up to high, goes through the resistor to low. All right. Now, this is important because we want to talk about how we place an ammeter in the circuit. If we look at an ammeter, we'll be drawing them like this. It's going to be a circle with a capital A inside. Well, if I want to measure the current, let's look at the gravity. If I want to measure the current in this river, where would I place the ammeter? I'd place it in the river, wouldn't I? So I would take this thing and I'd put it right here. That's going to be A1. Okay. Now, I don't really like my diagram that much. Instead of saying the whole hill is the resistor, let's say the resistor is like some pile of stuff here, right? That's slowing the river down. It's like a dam of some kind. It's slowing the river down. Well, putting the ammeter here would be the equivalent of putting the ammeter here, A1, to measure the current. Charges come out, go through the ammeter, through the resistor, past the resistor. What if I put a second ammeter here, call it A2? How would the currents compare? Well, they actually should be the same. Think about it this way. If the current here was greater than the current here, more is going in than is going out, and therefore we have a piling up of water. If the current here was greater than the current here, if the current was greater here than here, we would have a lot of water leaving here, less water coming in here, so we'd end up with a bit of a drought here. But this is not a perfect analogy. We imagine that this runs for a lot of time so that the water equalizes. You'd end up having equal flow. Well, that's no different than here, if this is A2. So I can state here that the current in 1 is equal to the current in 2, just like here the current in 1 is equal to the current in 2. So when we place an ammeter in our circuit, this reveals something, which is that the ammeter has to be in the path of the current to read the current, and that in a single branch like this, the current will be the same everywhere. Okay, so the meter needs to be in the path of the current itself. And then the next thing is, well, think about this. Imagine that the ammeter had some resistance. Wouldn't it slow the water down? Imagine when I put this, the ammeter would be the equivalent of a water wheel that spins and counts the number of spins and tells how fast the current's flowing. If that thing had a lot of resistance, I would slow the water down, right? And so by putting the ammeter in the circuit, I change the properties. Well, that's no good, right? I want to maintain the same current. I'm trying to read it. Same things here. And so therefore, I can say that to build this thing effectively, the resistance has to be approximately 0 because I don't want this thing affecting the circuit. All right, so that's my ammeter. The next thing is my voltmeter. Where do I place the voltmeter in the circuit? Well, let's think about this. When I measure the voltage, I'm essentially measuring the height here, right? I'm taking this thing and I'm putting it here, right? I could also take it and I can place it here. This piece of wood's getting in my way. I can measure from here, where the water starts, down at delta V to here, can't I? And shouldn't those two things be exactly the same? Right? Shouldn't those two heights in the analogy be the same? And in order to measure them, don't I have to start at the bottom and extend to the top? Well, if it was actually a voltmeter, what I would be doing is I would have to branch off of an element like this and connect it like that. That is the equivalent of me measuring from here to here. Here to here is like here to here. Now, here to here, measuring from here to here would be like measuring from here to here. So I can take another one and put it like this. And I will call this voltage of the source, and this is the potential difference of the resistor. Okay, let me just add this in here because I forgot to. Okay, there's my voltmeter. That's how I'm going to use it. I need to put it around the element that I'm interested in, and we'll notice again that just like here, delta V equals delta V, I can say that Vs equals VR. I'm sorry, I know I'm running out of space, and I hope that you're able to see this on your screen. I'm just clumping things up too much. For the voltmeter, we need to place it around the element where interested in. Okay. And next, when it comes to the resistance of the voltmeter, if we were to build this thing, well, imagine here. Imagine I had my meter and I measured from here to here, and that was a really low resistance path. Well, then the water wouldn't want to go down the hill. It would just fall back down, wouldn't it? Here, if I have this be a very low resistance path, the current's not going to want to go through the resistor. It's just going to go through the voltmeter. I don't want to change the current through the resistor because then I change the properties of the properties of the circuit itself. And so I want the resistance of the voltmeter to be approximately infinite. I want it to be very, very large. Okay, so that's how electrical meters work. Again, we'll tie this all together and things will start to make sense. Okay, so here we have our sample problem. Bulb rated at 5 watts with a delta V of 14 volts. So this is like the standard that's given, much like a 60 watt light bulb has a 120 volt standard. Then we say that the voltmeter here measures 19.5 volts. First thing is solve for the bulb's resistance, assuming that it's ohmic. Well, P equals V squared over R. From here, we get that R is equal to V squared over P. That's going to be, well, which V do we use, 19.5 or 14? Well, at 19.5 volts, the bulb will not have a power output of 5 watts. It only has 5 watts at 14 volts. So we want to use 14 volts squared over the power of 5 watts. And what we end up getting there is 39.2 ohms. Okay, this is why it's important for me to say assume ohmic also, right? Because when I increase the voltage to 19.5, we need to assume that the resistance is the same, even though factually it is not because the temperature increased. But for the sake of this presentation, we will assume it is. Solve for what the ammeter reads, right? Well, the ammeter is here. That ammeter is going to solve for the current in the circuit. Remember, the current at any point in this circuit will be the same for this reason here, right? If a dam builds, eventually the current equalizes at all positions. Well, Ohm's law, V equals I times R, right? I is equal to V over R. This is going to be equal to, again, 14 or 19.5. Well, this is the actual source, right? Not that. This is the standard that we determined this from. The actual source is 19.5. So we have 19.5 volts over 39.2 ohms. And this comes out to about 0.5 volts, which is really, amps, which is really nice, half an amp. Solve for the power output. Well, power is IV, right? Well, that's going to be 0.5 amps times the potential difference of 19.5 volts, which comes out to 9.75 watts. Now, right, think about this. We've increased the voltage. We expect a higher power. We expect more than the 5 watts. All right, so that's it for this lesson. I know it was a lot to take in, but as you do practice, I promise this stuff is going to become clear. And please come to the office hours to ask any questions you may have. Have a good day.